Epic. Epic! Epic Stat Tool 1 speedruns of Statistics! Brian Stevens! Versus Chapter 19, Comparing Counts. Begin!
Hey everybody, how are we doing? Good to see you here, Caitlin. Woo! Doing these speedruns live is pretty busy. Oh, let's get the comparing counts up right here as we get started on this next speedrun. So I want to make sure everyone knows that this is 30 minutes dedicated, or about 25 minutes because we have to prepare for the next one, as I figured out. This is 25 or so minutes dedicated to kind of quickly reviewing the chapter, but please note that these, as the warning says at the start, are not meant to be a full review. Please check out the videos where I do like a full chi-squared test. Please check out the chapter reviews. You can't learn everything in 25 minutes. This is meant to show you what you need to cover. If you hear something and you're like, I have no idea what Brian's talking about, I don't know what the chi-squared test of independence is, that's where you go back and review the notes. This is a speed run right here, so little different kind of learning objective than, this is meant to fill in or show you where you have gaps in knowledge. That's why the warning is at the start. I'd hate for someone to be like, Brian, the speed runs are too quick. And I'd be like, that's the point. They're quick. They're fast. They're a speed run. Okay, let's do this. Let's start up this speed run right here. And good to see everyone here. Good to see you here, Cameron. Remember, throw some questions in the chat if you have it. You get to direct the speed run a little bit because you are here and because you are live watching the speed run. So we got the speed run ready to go. Let's start the speed run. So we have here the chi-squared test of independence. What is the chi-squared test of independence? The chi-squared test of independence is when we are comparing two categorical variables. So it's very important to note, whenever you see the following: if you see a mosaic plot, if you see a contingency table which has the numbers in it, if you see, and we wouldn't have numbers quite like this, sure, that'd be 4, that'd be 6, that'd be 3, that'd be 7. I think I've done it. So if you see the following information, you are looking at two categorical variables. The chi-squared test of independence is going to have two categorical variables, which creates this idea of these counts. That's what we mean by counts. Like whatever groups these are, there's one person in this group, there's 3 people in this group, and we'd get a contingency table right here and a mosaic plot, which are bivariate displays of categorical data, which give us counts of observations for who's in each group. What would be an example of this? Well, classic questions like, what grade level are you at UT? Do you own a pet? Do you want a pet? And the answers to these questions are going to be things like freshman, sophomore, junior, senior, which is categorical, and sure. And then, do you own a pet? Yes or no on this. So here, we would have the following. We'd have a graphic that looks like this right here. And so there would be groups right here with yes and no. And we'd have freshman, sophomore, junior, and senior. And there we go. And that's what we get. And then we get a mosaic plot over here. Sure, let's see. I'd probably do it this way. And then you'd have people owning a pet. Maybe it's more likely as you go towards the senior level. And that's what we're kind of looking for right here. Like if we have down here, we put the no. Well, let's reverse it. We're looking, and we'll talk about this in a moment, to see if the two groups have an association. And that's what the chi-squared test of independence looks for. So we think right here, we're comparing two variables. And you can see right here, as people go to later years of college, they're more likely to own a pet. Probably because you're living off campus, there might be a lurking variable, which is something outside of these variables that is kind of controlling for it, that people on campus might be less likely to own a pet. But also we see that it is associated with, or at least via these graphics, it looks like it's associated with living or being an older student, or a student who's higher in progression through UT. So the null hypothesis for the chi-squared test of independence is one of my favorite ones to do. Whenever you write the null, what is the only word we put between these? The only word we put between these is going to be what? The only word we put between these, whenever you're writing the null hypothesis right here, you just put the word independent. So independent, I spelled properly, I think I did for once. Independent. So this is independent of this. And we can take a look at any sort of test we're doing. We're going to pull up a little bit of data right here. I'm going to get it. We'll go to the main screen. Oh no, Caitlin, what's wrong? Is the stream having problems? I don't see it. I saw a sad face. So, sure. Is weather independent of it being a holiday? Oh, that's all right. I got worried. Don't worry, I'm watching the chat at all points. So is weather independent of holiday? So all you do, and I want to repeat this again and again and again, the way to know this instantaneously when you see a graphic like this right here, all we do, no worries, is we just write independent. The null hypothesis is weather is independent of holiday. That's it. So you go right here and you just do the null hypothesis. And you go null hypothesis, weather is independent of holiday. That's it. Alternative hypothesis is going to be weather is not independent of holiday. You can also say is associated with. That's another way of doing it right there. So it's either independent or there's some sort of association, some sort of relationship between the two variables. But the null hypothesis is chi-square test of independence is it's independent. But we do have different ways of stating the alternative. Another way is to say it's associated. And of course, one other way, there we go. Oops, change the formatting. Sure. So the null hypothesis is that it's independent. You could also say is dependent on a holiday. So the weather is dependent on holiday. I just like to say it's independent. It's not independent. But there are other ways of stating the alternative. But just think of what this means. They tell you nothing about each other. Let's look at our previous example right here where we were talking about somebody's year at UT and whether they own a pet. Here, we'll go back to Speedrun board. Wrong button. It's not Wacky Wednesdays. So here we are where we have the null hypothesis. Let's bring it back on the screen right here. And the null hypothesis is always that things are independent. And here we are with our is owning a pet independent of your grade level. When you look at this, it seems to me like that there's evidence of an association. Do you see the evidence, all the Mario? Do you see the evidence of the association right here? That as somebody is a later year at UT, it looks like they are more likely to own a pet. These are people who do own a pet, yes. And we see when people are senior, this is just fake data that we made up, it looks like around 70% of people own a pet. And we'd see that over here in the contingency table where maybe 70 people own a pet and 30 people don't out of 100 people total. So you would see this where for freshmen, maybe we collected a similar sample size where only 10 freshmen own a pet and 90 don't own a pet out of 100 total. And we're viewing that right here where the 10 own a pet versus we're viewing over here where the 70 own a pet for seniors. And this looks like a strong evidence of an association. Exactly. Caitlin's pointing out probably like the lurking variable that they are off campus and not living on campus. So when you think about this, what would you do here to the null? Now, we don't have a p-value for all this right now, but when you look at this, you'd be like, well, that looks like there's evidence that they are not independent, that they're associated with. So your grade level at UT and owning a pet might be associated. And that's what we see down here in this one. It looks like evidence of an association. And it looks like the higher up grade level you are, the higher the probability of you owning a pet, that it's more likely that you own a pet when you're in later years at UT. So that is how we do the null and the alternative. And I lost my sheet for the chi-squared. Here we go. We're back to it. Condition check. Condition 1. Hopefully no one gets bored. No one gets bored of crab raid. So condition 1 is random. That means we need to randomly find these students. We can't just go to the students at like the Bunny Appreciation Club or the, I don't know, at least we have Bunny if you didn't know. So we can't go to like a pet appreciation club. We have to go to random students at UT and talk to random students. So I always like to do this as condition 1 right here. Condition 1 random, randomly collect your data. I know it's not condition 1 here, but it's a condition we always have. Condition 2, less than 10%. We have to talk to less than 10% of UT students. And this is where the conditions get a little bit different. Condition 3 right here is expected cell counts must be larger than 5. So what is an expected cell count? Let's talk about this. Okay, so in our sample of UT students, let's make up another set of data right here. We have that, Here we go, yes. Here we go, no. Let's say 100 students own pets and 100 students don't own pets. Does that make sense? Pause. Pause when we get to condition 3 because it's going to change. It depends on what you're doing. Great job right there, Kaylin. And so we have here freshmen, sophomores, juniors, seniors. Now I want you to think about this. Don't think too hard on it because you'll be like, oh, I think I know. If we talk to 50 freshmen, 80 seniors, 120 and 150. There we go. I don't know. For some reason, we talked to more seniors. I don't know. I don't know where we collected data, but we talked to more seniors for some reason. Is it random? I hope it is, but we'll say it's random. For some reason, we just talked to more seniors. Maybe they were just more gregarious. And I was using numbers I could easily calculate. Oh, well, then we have to change these numbers. 2 seconds. Okay. Do you notice that half the people own pets and half the people don't own pets? Let's just notice that right now. Like half the people say they own pets, half the people say they don't own pets. We talked to 50 freshmen. I haven't told you how many freshmen own pets. How many freshmen, and put this in the chat, see if you can figure this out. How many freshmen would you expect to own pets? How many freshmen would you expect out of the 50 freshmen? Since we know half of people own pets, we talked to 50 freshmen. How many freshmen would you expect to own a pet? This is what an expected cell count is. If you know that half of the people own pets and we talked to 50 freshmen, well then how many freshmen would you expect to own a pet? Well, don't go by your knowledge here. You might say, well, I don't think it's likely they own pets, but how many would you expect if half of people own a pet and we talked to 50 freshmen? Half of the students we talked to, there you go, Kaylin. I think, Kaylin, you're going with like what you would believe if you didn't know the data, but the data says half of the students own a pet. So we know half of the students own a pet, and we know that we talked to 50 freshmen. So the formula to do this is column total, row total times column total over, I hate color change pens, over grand total. And I kind of reversed the numbers. Let me put the 400 down below. So I'm going to take this 400 right here and bring it down here because it's the total. And it's row total times column total over grand total. I know. And so row total, I was like, that's probably right, but, or closer to the truth. Row total times column total over grand total. So this is row total times column total over grand total equals to expected cell count. And we've drawn the formula right here. Just to do other ones real briefly right here, how many sophomores would you expect to own a pet? So just change your numbers. How many sophomores would you expect to own a pet? So we're just doing the row total times the column total over the grand total. So how many sophomores would you expect to own a pet? You just kind of cross in on it. You go here and you go this, as long as you can draw on it. You go this and this right here. You just cross in on it. 40 exactly. Let's change the numbers a little bit to make it more difficult. Let's say only 20% of students own a pet. So we're changing the numbers right here. And remember, only 20% of students own a pet right now. See if you can solve this. So with only 20% of students owning a pet, 80 would own a pet. And see if you can solve right now. We change the numbers. How many sophomores would you expect to own a pet now? So remember, we're just doing the same sort of formula right here. I'm solving in my head. I want to see if you can solve it. Great job, Ashura. Great job. So how many sophomores would you expect to own a pet now? See if you can solve it. I'm solving it in my head. Hopefully I've done everything. Oh, wait. I have a wrong number right here. But it won't change it. That should be 320. Correct. Amazing work. We're going to throw out some points. We're having a little fun today. Great job. Give you some good points right here. So there you go. So I think Mubot's still with us. So you would expect 16. And just think about that. That's 20% of 80. But you can solve the formula right here. What would you want to check right here? Ooh, and I think we pass it. You'd want to make sure that all of the expected cell counts, and this is the condition, all of the expected cell counts are greater than what? What is the condition for all of these expecteds that we're calculating? And we'd want to calculate the smallest one. So I'll write the expected right here. That's 20% of that. That should be 10. That'll be 40. That'll be 16. These are all the expecteds. I'm trying to calculate them all in my head. Please tell me if I make a mistake. These are all of the expected counts. They're not what we actually see. They're all of the expected counts. And please tell me if I make an error. That should be correct right there. That's 120. So if you were practicing calculating all the expecteds, See if you can calculate all the expecteds right here for any of these. And this is what we would expect. What we observe may be very different. We could observe that no freshmen own pets, or that, yeah, that would be correct. No freshmen own pets and 50 do. And we could observe right here that 20 own and 60 do not. So that would be the actual observed right there. Does that make sense? Like what we're calculating there in red is the expected, and then what we would have what we actually observe, which we would say we observe 0 students owning a pet who are freshmen, but we expect via random chance for there to be 10 students who own a pet who are freshmen. So make sure to know that right there, checking the expected cell count condition. So we just did the hard condition to check. You have to do the row total times the column total over the grand total for every single cell, or just the smallest cells to see if it passes. That's how we get an expected cell count right there. But the easiest condition to check is to check to see if they're count data. How do we check count data? All count data is, we just look to see if both variables are categorical. By virtue of us having these graphics, we pass. I wouldn't say because, you could. Mosaic plot has to be categorical data. So because we're doing categorical data, it is count data. So that's the count data condition right there. So is our previous example with pets and year at UT categorical? Yes, because owning a pet is category. Yes, no. And your year at UT is a category freshman, sophomore, junior, senior. So we have 2 categorical variables. So the way to check this right here, the count data condition is 2 categorical variables. And if you have 2 categorical variables, you're good. Calculations, rows, columns, and grand totals. We were seeing that previously right here, where we have the rows right here, the columns, and the grand totals. So here's the grand total. Here's the row totals right here. There's the row totals. And then there's the column totals up here across the top right here. These are the columns. This is the rows. And these are the grand totals. So I'd have to watch out if I'm solving these numbers. I'd need to make sure they add up properly right here so we get the right numbers. Expected cell counts. We were doing some expected cell count calculations. Let's do a practice one here and jump. I think we just took a picture of one. Let's see if you can solve out. This is good practice. Let's go to the main screen. Can you solve out the expected cell counts? Take a moment right here in this video. A lot of times we like to blank out one of these. So see if you can solve an expected cell count. I'll ask it's not going to be nice numbers. What is the expected cell count for no rain, no? What is the expected cell count for no rain, no? So I'll show you how to do it right here. What is the expected cell count for no rain, no? So what is the expected cell count? I'll highlight it. For no rain, no. And I'm going to pause here in the video so people can solve it. Can you solve the expected cell count for that one right there? How do we get the expected cell count? So remember, here's the steps. Cross in on it. So now we know what numbers we have to use. Now circle those numbers. That's the row total, column total. Multiply them and divide by the grand total. Once again, row total times grand total. That's what those stand for. Oh my gosh. Row total times column total over grand total equals to the expected. That might be right. Great job right there. Good practice if you got it. Yeah, that sounds about right. Excellent work. And let's go right here. Let's do 400 times 301 divided by 413. And excellent work. Great job right there. Really close. So Cameron, you got it correct. Just double check your work. Make sure I typed it in correctly. We can also check our work and jump. Good guess right there. We're going to throw out some more points to the viewers. Be practicing along, see where your error is, and then the practice makes perfect. That's what we do. And so let's go ahead and take a look at it in the jump output. We'll see if we got the right answer. It is 291.52. That is 400 times 301 divided by 413. So double check your work right there. Practice, and get it down. Perfect. The next thing we should be calculating should be a chi-squared, probably, I would assume. Let's take a look. Expected cell count we just did, and the chi-squared is what we're going to do next right here. So the chi-squared is the observed. We're talking about this one right here. Observed minus expected. You take that quantity and you square it, chi-squared. Observed minus expected. And then we divide by the expected. I just want to say thank you so much for everyone practicing. If you are trying to solve these with me, you're getting some great practice. Yeah, it should. And please tell me when you look over your results, if you get something wrong by like a decimal, I'll fix it. Unless it's unless it's like one of those things I'm like, that's actually a big error to be off by a tenth. Like sometimes there are questions where a small error can be big. Let's find the chi-squared for this one we just found. So remember the chi-squared formula is observed minus expected squared over expected. So let's find the chi-squared. Let's find the chi-squared for this cell. What would be the cell chi-squared for this? So it's important to know when you look at this that this is the observed. So in the chat, start figuring it out right here. This is the observed. That is the expected. So the count is the observed. So we want to do the observed minus the expected, which we see on the screen right there, squared over the expected. And this is the cell chi-squared right here. So what would the cell chi-squared be? Observed minus expected squared over expected. So I'm going to start writing it out, see if you can solve it. It's good practice, even though I'm going to write the numbers. It's going to be pretty, it's going to be very small, actually. There we go. So what is it going to be? That looks, Caitlin, great job right there. That looks, it's going to be very small because we're dividing by some small numbers. Great job. So let's go minus 290 squared. I already had it in there, and divide by. Great job, Caitlin. Perfect answer. Yep. And the good news is if you do this practice, you can always do these in jump. If you have data, which we have some data from our data sets, like if you still have jump on your computer, which you should, you can just go here and then check your work by going to the cell chi-squareds, and it did round it up. It's probably carrying more decimals than we are in the background, and that does round up right there. So Kaylin, that'd be perfect for the test right there. You got it exactly correct. So great job on a cell chi-squared. That is the cell chi-squared. Excellent work right there. Do I still have it saved in the chat? Oh, I don't have the number saved. So we'll throw out some more points. We're just getting a ton of points today. So next, let's take a look at the next thing we're going to cover right here. So here we are. The chi-squared test statistic. So what it means when the chi-squared test statistic is large. So the chi-squared test statistic, how do we get this chi-squared test statistic down here, which is the Pearson? The Pearson has your p-value. Memorize that. The Pearson has your p-value. When doing the chi-squared tests, you're using the Pearson. So when we look at this result, it's important to know that with your cell chi-squareds, someone should be saying it. If you know this, you'll be like, oh, wait, we're going to take all the cell chi-squareds and we add them up. If you add up all these numbers, you get the following number right here. So when you add up all of these numbers, you get the following number. But we then need to take this chi-squared and plot it on a distribution, on the chi-squared distribution, and it would look something like this, where we have 33.35% shaded. That is the p-value. This right here is the p-value, which is the area shaded on the curve, with a chi-squared with 1 degree of freedom. So I love doing this. This is one of my favorite things to practice with people, is the degrees of freedom for the chi-squared. When we talk about the degrees of freedom for the chi-squared, you'd say, Brian, this is a what by what right here. Look at this and say, Brian, this is a what by what. You only want to look at how many things there are right here. Brian, that's a what by what. Brian, that is a what by what. So you look at that, you say, Brian, that's a blank by blank. Don't look at the totals, because that's not a group. There's this many groups for this, and there's this many groups for this. It's Caitlin's got the degrees of freedom. Brian, that's a 2 by 2. There's 1 degree of freedom. 2 by 2, and you drop each finger by 1. 1 times 1 is 1. So how about our previous example? So see if we can do this one here. Brian, that's a what by what. So start off by saying, Brian, that's a blank by blank. Don't look at the totals, but look at this and say, Brian, great job, Turner, right there. Brian, that's a blank by blank right now, and then tell me the degrees of freedom next. And I'll do a more complicated one after this. Brian, that's a blank by blank. And so Brian, that's a blank by blank right there. We'll end with a complicated one, but I'll show you what to do with the degrees of freedom. Brian, that's a blank by blank. So you should be looking at how many, Brian, that's a, Brian, that's a, exactly. Great job. Turner right there. Why would it can be 2 by 4 or 4 by 2, and then Kayla does it. So either which way is fine, because if you reverse it's 2 by 4 or 4 by 2, either which way is fine. But so as long as you know there are 4 in one group and 2 in another, you can then subtract and get the following formula: 4 by 2 reduced down 3 times 1. Does that make sense right there, Cameron? It doesn't matter if you reverse it, because the multiplication is going to be the same way with the 3 times 1 or 1 times 3, whichever way you do it right there. And we can see this. I'm going to bring up some stuff in jump right here. So let me open up a bigger jump data set. Is this... Good. We got it. Okay, so this one right here, I'm going to do more. Let's do distance from campus and your family order. Okay, I want you to look at this right here and say, Brian, that is a what by what. Be very careful. Okay, figure out the degrees of freedom for this. If you can figure out the degrees of freedom for this, you are definitely on track. So Brian, that is, and never get tricked by the total columns. Like if you look down here, you'll see the total columns, but you'll still see. Okay. So what is this? This is a what by what. Brian, that's Caitlin, great job. We're throwing some more extra credit. That's exactly what I want people to say. Brian, that's a blank by blank. That's exactly, when I teach this in class, I have people saying, Brian, that's a blank by blank. So Brian, that's a 4 by 5. So that's a 4 by 5. So for some reason that's the hard part. And then you reduce each finger by 1. If people are wondering what we're doing, 4 by 5 turns into a what by what. Because we're going to reduce each row and column by 1. 4 by 5 turns into what by what? Oh, running out of time. 4 by 5 turns into Ashura, and please tell me if I'm pronouncing it incorrectly. You are correct, and great job. That is correct. You just figured out the degrees of freedom. You just did it. Excellent work right there. So 12, perfectly. 4 times 3 right there. So 5 by 4, 4 times 3, 12 right there. Excellent work. And that's how we get the degrees of freedom. You just reduce each one. So you reduce each hand by 1, which I'm trying to do right there. 5 by 4 turns into 4 times 3. So excellent work. And then, yeah, great job. I love seeing that excitement right there. Last but not least, we take that chi-squared test statistic and we do the same thing we've always been doing. If you remember from just a moment ago, we had a chi-squared with 1 degree of freedom and I drew it on the graphic. And I think the test statistic was something like this right here. It's very close to that because I'm getting close to the p-value. It must be right about there. And so we go back and we take a look. Where is that graphic at? Look at all these sheets we'd opened up today. Oh, it's got to be near here. Oh, well, we have lost it to the... Oh, there it is. 0.935. 0.935. And if we put that in right here, there's the p-value. This p-value here is very high, and thus we fail to reject the null. So we would not have evidence for the alternative. So you just subtract 1 finger from each end. Exactly. If you get something much bigger, then you would just like, we'll end with my classic question here about chi-squared degrees of freedom. If we were to ask people, like, favorite restaurant has 30 answers, and then favorite ice cream has 21 answers. I'm going to make this easier on myself. I'm going to put 31. That makes my life way easier. So how many degrees of freedom for this test? Who can answer this right here? How many degrees of freedom for this test right here? And then we'll be doing the next thing right here. How many degrees of freedom for this test? Join me in the next video here soon. So we asked people their favorite restaurant, and we would see if that's independent of their favorite ice cream flavor. So what would you do right here? Because now you don't have enough. I don't know. You probably don't. So you can invite over all your friends and have them hold. Well, the final correct, Caitlin. There could be screenshots of jump output like we have previous, and that's why we looked at some screenshots here. There definitely can be screenshots of jump output right here where we fail to reject the null hypothesis because the p-value is well above 0.05. And great job, everyone in the chat right here. So this chi-squared test statistic, we would go, if we were doing all the steps, and go over here to the applet to plot it. And the chi-squared is the sum of all the cell chi-squareds. Turner, great job. 600 for that random question I asked right there. All you do is just subtract 1 from how many levels there are for each. So since you say, Brian, that is a 31 by 21, and that means degrees of freedom equal to 30 times 20. And that's why I picked this, so I could do it in my head. Look at this. Great job right there. This is the degrees of freedom for the chi-squared, which is different from the other ones. I think we've covered everything for this. I feel like we're... Oh my gosh. We've done the conclusion. We've done the interpretation of p-values are the same. Chi-squared, never causation. Let me just say this flat out. If you're at the end of this video right now and you hear causation in something, we never use causation in statistics. We're not talking about causation. We've looked at an applet. Oh, there's the applet. That's my favorite applet. Wait, did I just close out everything? Oh no. I think that's got it. Join me for tools and techniques in business analytics. Let's have some fun. We're going to end this stream right here now. We're going to go over, we talked about the chi-squared. Make sure to check out the other videos, which might be longer, but I'll see you over there. Good seeing everyone. We've got a group joining from video to video. Next video starting in about 4 minutes. See you soon. Bye for now, everyone. Bye.